Here we go, video 3.4. We're going to be learning today about weight and mass. In the last video, I probably confused you because in the last video I said we've already learned about mass. Nope, we had not. We're going to learn about it today. So I'm sorry if that confuzzled you. Confuzzled, not a word. All right, so here we go. Here are those same two definitions of mass that I gave you last time. So remember, in chemistry, we always define mass as a measure of how much matter makes up an object, right? Literally just counting protons, neutrons, and electrons. More protons, neutrons, and electrons means more mass. In physics, we define it according to inertia, right? The more mass an object has, the harder it is to get the object moving, right? The more mass it has, the less its velocity will change when you apply a given force to it, all right? Please notice that the object's mass is a property of the object itself. No matter where the object is, it's still going to be made up of the same number of molecules, protons, neutrons, electrons, and whatever, right? So the mass of an object stays the same no matter where it is. This calculator here is about half a kilogram. If I take it to the moon, still a half a kilogram worth of molecules, right? All right. Units for mass, as I said in the last video, are kilograms. If I ever give you grams, I'm a jerk and you need to convert to kilograms. Please remember, 1 kilogram equals 1,000 grams. Cool? Cool. All right, now weight. I gave you this definition back when we first learned about forces, but I want to reiterate because it is very important. So weight is the force of gravity acting on an object. Again, I've got half a kilogram worth of calculator here, right? That's how many molecules are in it, all right? When I let it go, it falls because gravity is pulling it down. The weight is a measure of how hard gravity pulls it down, okay? So, why do we have weight? Well, because of gravity, right? The reason we have weight on Earth is because the Earth has a gravitational pull. This pull pulls us and all objects on the Earth toward the Earth's center. That's why things fall when you drop them, right? It's also why your feet get tired if you stand all day, right? Because gravity's pulling you down all day long, but the ground is pushing up on your feet, and that upward force on your feet begins to hurt by the end of the day. Now, if you go to the moon, still 500 grams, sorry, half a kilogram worth of calculator, but there's less gravity. So if I drop it, it'll fall more slowly, and your feet won't get as tired by the end of the day because gravity's not pulling you down as hard. So the floor doesn't need to push up as hard. All right. Now, if you go into the deepest reaches of outer space, like way beyond poor Pluto, then you're far enough away from the sun and, you know, whatever other planets and stuff that there's essentially no gravity. Okay. And so you float when you're way out there because there's no gravity, but still half a kilogram worth of calculator. Okay. Quick side note, astronauts in orbit around the Earth do float. And so they are weightless, but there is still gravity there, all right? And we'll talk about that more when we get to circular motion. So to actually have no gravity, you got to be way out in the middle of nowhere, all right? Now, because of this, notice weight is the force of gravity. So from now on, when you hear the word weight, you should think, oh, well, that's just force of gravity. Why is my pen not writing anymore? There we go. So you should just think, oh, weight, that's the same as force of gravity, okay? Because weight is a force, we measure it in newtons, okay? Or pounds if you're not using the metric system, right? So mass is going to be in kilograms. Force of gravity, weight is in newtons. All right? Now, in Europe, when if you ask somebody, hey, how much do you weigh? They're going to give you their weight in kilograms, which is wrong. Dear Europe, you're making it harder for me to teach physics to my students. So when if you go to Europe and you say, how much do you weigh? And they say, whatever, 60 kilograms, that's not really their weight. It's actually their mass. But on Earth, it doesn't really make that big of a difference because it turns out that for a given planet, Earth, weight and mass are proportional. An object with double the mass will also have double the weight. Okay? Triple the mass, triple the weight, etc. So it says, let's see, on Earth, if Roy has twice as much mass as Sally, he also has twice as much weight. So on Earth, Roy's mass is 90, Sally's mass is 45. Okay? Roy's going to weigh about 900 newtons, Sally's going to weigh about 450. You'll notice they're double, right? On the moon, we get the same thing. Same masses we had on Earth, But notice they weigh less, but still double. Okay? And then in outer space, way outer space, double the mass, but no weight because no gravity. Okay? So mass measures matter. It measures inertia. Weight measures force of gravity. Notice in outer space, if you want to cause Roy and Sally to speed up, like use rockets or something to get them moving, Roy's still going to be harder to move even though there's no gravity, right? Because he has more mass. All right. So in chemistry, you probably learned that 454 grams is a pound. And that's true on Earth, okay? If you go to the moon, 454 grams is only about a sixth of a pound, 0.17 pounds, right? Because there's less gravity on the moon, and so that same amount of mass will be pulled down with less force. All right, so what is the exact relationship between mass and weight? So here is your one new equation for this video. Weight, the weight of an object, is equal to the mass of the object times the acceleration of gravity wherever you're at. Force of gravity is mass times acceleration of gravity, right? Because if I drop my calculator, it's going to fall because the only force on it will be gravity, the force of gravity, and that force of gravity will produce the acceleration of gravity, okay? So on Earth, the acceleration of gravity is negative 9.8 meters a second squared. Always, that's the acceleration of gravity, okay? Now, force of gravity depends on that acceleration of gravity and the mass, okay? Similarly, on the moon, the acceleration of gravity is always negative 1.66 meters a second squared, but the force of gravity will still depend on the mass, all right? My point here, what I think I'm not doing a great job expressing here, is please make sure you understand that force of gravity and acceleration of gravity are not the same, right? Acceleration of gravity is negative 9.8 meters per second squared, whereas the force of gravity is your weight, and that's going to depend on the mass. Cool? All right. So let's do an example. A dog has a mass of 30 kilograms on the Earth. Let's choose a different color here. A dog has a mass of 30 kilograms on the Earth. The moon's acceleration of gravity is negative 1.6 meters per second squared. Find the dog's mass on the moon. Mass doesn't change. So his mass is still going to be 30 kilograms because he's still 30 kilograms worth of molecules. What's his mass in outer space where there's no gravity? Still 30 kilograms. Now, what's his weight on the Earth? Now I'm asking you for the force of gravity. So that's mass times acceleration of gravity. So the dog's mass, 30 kilograms. Acceleration of gravity, negative 9.8 meters per second squared. Multiply, you get negative 294 newtons. Negative? That's weird. Technically speaking, if we can stick with down being negative, the force of gravity is always going to be negative, right? Because gravity pulls stuff down. All right. Now, if I say to you, how much do you weigh? You're not going to say negative whatever, right? So it's just sort of understood, right? But technically speaking, that force of gravity has direction and it is down, which means for us, very frequently, our force of gravity will be negative. All right. Now, what's the dog's weight on the moon? Well, it's going to be different because the acceleration of gravity is different, right? So 30 kilograms times our new acceleration of negative 1.6 meters a second squared gives negative 48 newtons. So that dog weighs less on the moon than it does on the Earth. And the dog's weight in outer space, 0, because no gravity. All right? So in this problem, I gave you the mass and we defined the weight. Sometimes we go backwards. So here we have a cow that weighs 5,000 newtons. So I'm telling you the force of gravity is 5,000 newtons. Oh, don't forget, gravity pulls stuff down. Bam! Don't forget that negative sign, right? Okay, and then I know the acceleration of gravity is negative 9.8 meters a second squared. So now I can use this guy, Fg equals mag, and solve for the mass, right? So I'm going to go, well, let's just do this. Mass is Fg over Ag. So our force of gravity is negative 5,000 newtons. Acceleration of gravity is negative 9.8 meters a second squared. Notice the negatives do cancel, and you get a number that I forgot to write down, so you're just going to have to wait. 510 kilograms. There you go. All right. I think that's all I got for you. I do. Hooray. Or it is.